Hello everyone. Today I look a little bit smaller. That's because the board went up, or I hope so, because I didn't get any smaller, I thought. Today we're going to look at a wakeboarder that's going in a certain angle in the water, and we're going to look at what forces act upon it and at which angle the wakeboarder has to wakeboard to keep himself upon the surface of the water. First, it is good to draw the situation just like always. Here I've drawn myself on a wakeboard. You can see I'm very happy. I love to wakeboard. Yeah, we want to calculate what the angle is between the wakeboard's surface and the waterline, which we call angle theta. The forces that act upon on the person and the wakeboard that are the drag force of the air of the water on the wakeboard, the gravitational force because the person and the wakeboard have a certain mass, and the buoyancy force. And the buoyancy force is the force that is exactly why boats float. Here are the constants that are needed to calculate the buoyancy force and the drag force. The buoyancy force depends on the density of the water, the submerged volume of our object, and the gravitational acceleration, while the drag force depends also on the water density, a certain constant that is specific to the shape of the wakeboard, the area of the wakeboard, and the velocity that the person and the wakeboard goes. I'm standing on a wakeboard, and the forces that act upon me that are the buoyancy force, the gravitational force, and the drag force. While the drag force is at a certain angle, while this angle between the buoyancy force and drag force is exactly theta. I don't want to sink when I wakeboard, so therefore the gravitational force needs to be counteracted by the y component of the drag force and the buoyancy force. So therefore the gravitational force is equal to the buoyancy force plus the drag in the y component. So that is also another thing that we need to calculate. So the drag force in the y component, drag y, is equal to a half rho of water times a constant times the area times velocity squared. And now we have to take the y component, and we know this angle, and we know the total length of F drag. So therefore, and this is the total length of the drag force, so therefore we need to multiply this by a cosine of theta. Also, another thing that we want to know eventually is the area that the wakeboard is in the water, which is this area. And this area on the other side of the wakeboard doesn't contribute to the drag force. So therefore the effective area, which we can call effective area, is equal to a half, because we can say that the half of the wakeboard is underwater and almost the half of the wakeboard is above water. So therefore is a half times 1 meter times 0.25 meters. So if we fill in this formula, we will get m of the mass in a wakeboard times g equals the buoyancy force, which is rho of water times v submerged times g, plus our drag force in the y component, so a half rho of water constant a times v squared times the cosine of theta. And now we want to solve this equation for theta. So therefore we take the buoyancy force, take it to the other side of the equal sign, and divide it by the rest of the drag force. So we will get m times g minus the row of water times v submerged times g divided by a half times the row of water constant of d area times the v squared is therefore equal to the cosine of theta. If we want to solve for theta, we need then theta equals the arc cosine of, for simple reasons, this can be filled in there. Another thing is that the area, we haven't calculated the area yet, but we can say that the area which is the length times the width, is the total area underneath the wakeboard. But the problem is that not the whole area underneath the wakeboard is submerged into water. So therefore we can almost say that the half of the wakeboard is underwater. So we need eventually a half of the wakeboard underwater, and which we can call the effective area. So therefore the effective area equals a half times 1 meter times 0.25 meters, which is equal to 0.125 meter squared. If we fill in those constants within the within this formula, and with the arc cosine function all over the other function, we'll get for theta almost 26 degrees. So my wakeboard has to go 26 degrees with an angle of 26 degrees at with the surface of the waterline to keep me upon the surface. Thank you for watching.